Recording then. Okay, go ahead.
Okay, so I just, so good morning to everyone. I just started on, I have a big file with all the stuff together, so perhaps I have to separate this into several lectures, but I've not done it yet. So, okay, so just a moment. Yeah, so last time we were talking about this weighted blowing ups. So I explained to you that this is a way, in some sense, to eliminate this phenomena due to the appearance of these pinch points. So the fact that you can have this pinch phenomena in along a formal curve. Yes, in some sense, it's a phenomenon where you have so this is completely impossible for in the case of analytic, let's say analytic sets or in the algebraic setting, but for vector fields, you can have this kind of a formal symmetry, which is not analytic, right? So this is the case where this is a symmetry of the solution of a vector field, but the solution is non-analytic. So it's for me it was a quite unexpected phenomenon, but in fact it appears, and you have to deal with this by this new kind of blowing up, right? So yeah, so I explained to you this weighted blow up. So the difference with respect to the usual blow up is that here you have to, in fact, take into account a symmetry which appears in your blow up space due to the fact that you have this. So of course, the blow up is nothing else than taking some torus action and then taking the quotient space of let's say Cn minus the origin by this torus action, and then the projective space is nothing else than let's say the quotient space for this torus action. So in this case where we blow up with weights, this quotient space should have some singularities of the quotient type, right? So in this case, I just explained to you when you take this action by, let's say the torus action by t to the square x and t y, and then you have to identify these points which are on the same parabola, right, above and below, and this gives you this identification, which is in some sense unavoidable in the quotient space. So along this line here, you see that you have these two branches of the parabola which are identified. So this forces you to have this symmetry, a singularity in the quotient. Okay, so I explained to you this orbifold charts, right? So this group of symmetries, as I said to you, is expressed on each orbifold chart by the action of the cyclic group. So the cyclic group which acts on each chart depends on the chart. So for instance, in the first chart where you makes x goes to the y to the power of omega-1, you have the weight. The group which acts is the z over omega-1z, the cyclic group of order omega-1, and then it acts linearly on the coordinates by this expression here, right? So okay, so we have to be used to deal with this more as, let's say, this generalization of the concept of a manifold, which is what's called orbifold. Now I think it's a very fashionable object because there are a lot of things which get simpler when you express this in language of orbifolds. For instance, when you try to understand the theory of the covering of Riemann surfaces, it's very interesting to consider orbifolds instead of, let's say, which are, in the case of Riemann surfaces, are nothing else than Riemann surfaces with marked points. So each point should be considered a point of ramification of some order, which is nothing else than the order of the symmetry group. Okay, I'm not going to repeat this, but roughly speaking, an orbifold is just some topological space which is covered by charts, but on each chart you have this information about the symmetry group which acts on the chart, and let's say the portion of the manifold which is covered by each one of the chart is homeomorphic to an open set of some Euclidean space modulo the action of this finite group, which is okay. So yeah, so one thing that I said is that I have to remember the group is part of the structure. So in fact, in some case, this quotient space M, it's don't have a singularity at all. So if you can even have a smooth ambient space as the quotient, but even in this case, it's interesting to keep track of this group actions because they give you information about the symmetry of the objects which are given in the manifold, right? So I just skip this. Okay, so I'm just directly going to the example again because yeah, sorry for this repetition. So
yeah, Daniel, a little
yes.
question. Yes, so in your case, in the case of blowing up, so the only groups which appear are simply Z over omega kz, right?
Yeah, so this is the first step, right? So if you start with a smooth ambient space, so this is just an orbifold where all local symmetries are trivial, and then you blow up, you are going to introduce this, at each point, this the finite groups will be the cyclic groups, right? Mm-hmm. But then you can iterate this procedure. So you get this now you have an orbifold and you want to blow up points on this orbifold, right? So now the center should be compatible also with the group action. And in this case, you can introduce more complicated finite groups by iterating the blow up of this orbifold.
Okay. Thank you.
Okay, so I think I stopped here with this example. I was a little bit quick in the last time, so I want you just to recall you a little bit. So this is the typical example where you can take advantage of the quasi-homogeneity properties of your vector field to, let's say, to choose the weight of the blow-ups in order to get a more simple object at the end, in some sense. I'm going to explain to you. So in this case, you have this initial part here, and then there is a rest term which will not affect at all the singularization procedure. Of course, it will be important later when you try to understand the foliation around the divisor, because of course, this term here has a strong influence on this. But for at least for the resolution of singularities argument, we don't have to take into account. So the quasi-homogeneity is given by the weights 2 and 3. So we blow up with these weights. So I recall to you so how do you transform this vector field? So the first logarithmic term, x d over dx, becomes x d over x minus 3y d over dy divided by all this divided by 2. So I simplified here, and the second term is skipped as is. And then we regroup the terms, and so okay, I've said to you that this rest term has a quasi-homogeneity order greater than this initial form. So this is expressed by the fact that you have an x square, which is going to be factored out on this rest term on the new coordinates. And in the initial term, you have this just a power of x, which will appear. So now there is this reduction procedure step where you divide out by x. Why? Because you want that the divisor is not contained in the nilpotent locus. So the way to eliminate all nilpotent points on the divisor is just by dividing by the highest power of x, at least in this chart, the highest power of x which can be factored out. And so in this case, this power is 1. And you get this expression in the first chart. And so, well, I made the computation on the second chart, so I'm not going to repeat, but so this is the y-directional chart, and you get this new expression, right? So as I said to you, you can verify that in one of the charts, let's say in the second chart, you have 3 singularities given by the 3 roots of unity here, which are on the divisor y equals to 0. And on the first chart, you have two singularities, right? So here I've made a real drawing because in the complex, okay, you see that in the complex domain, you don't see this, you just see one of these roots. Sorry, in the real domain, you just see one of these roots, but in the complex domain, you see both, all three. And in the, so you see here the cusp in this, let's say, this is the draw of the spherical blow up, right? So at the cusp, we have separated these two branches of the cusp, and each one of the branches now it's it lands into a saddle type singularity. So in some sense, well, have the singularized this in one blow up, right? But okay, so now let's study the symmetry. So as I said to you, in one of the charts, you have three. You see these three roots of the unity, but of course in the quotient space, this gives you this single black point here, which is the identification of these three singularities by the action of z over 3z. And on the other chart, you have the action of z over 2z, right? So there is two singularities which are precise. In this case, this is precisely the two singularities that you see here, because they are real in this case. And well, they get identified. So I don't know if you remember, I'm not going back to this, but I don't know if you remember, I've told you that in this case of this foliation, there is a way to classify the germ of the foliation just by looking at the holonomy along these two paths, which make one turn around each one of the singularities. Well, in fact, in this new setting, these are not singularities of the foliation, but they are in fact ramification points of the orbifold, right? So this round points here, I don't know if you can see my mouse, but this round points here are ramification points of your orbifold, and the only true singularity of the foliation is given by this black point here, right? So, so the leaf of your foliation, in fact, it's a sort of orbi leaf because it's just this projective space, weighted projective space, minus the singularity, which is the point S, which is the saddle, right? And the fundamental group of this leaf. So now it's an, as I said, it's an orbi leaf. So it has let's say it's not exactly the projective space minus 3 points, because, well, let's just make a drawing here. So consider, for instance, this path eta, which goes around one of the ramification points. So if you look at the ramifying coordinates, when you make 3 turns around the ramification point of order 3, then you close the path on the, let's say, in the uniformizing coordinate. So in this case, you have the relation that eta to the power 3 equals to identity, the same thing as the other one. And I don't know if you remember, but this is precisely the generators of the relation that I have in the generators of the holonomy group in the previous study that we have made of the cuspidal singularity using the usual blow-ups, but in that case it was not so explicit because we needed to do 3 blow-ups in that case, and these relations was given by some 2 other saddles which appeared on after these 3 blow-ups. Okay, so now I think I'm going to go a little bit, but here I just show to you the symmetries that we have for the 2 vector fields on the first chart and the second chart. So in the first chart, there is just this Z2Z over 2Z symmetry, and the other chart you have this order 3 symmetry given by. So you see that the group, it doesn't map the vector field into itself, right? Because there is this minus sign here. But this is due to the fact that, in fact, this vector field is not really a section of, let's say, of a tangent, the tangent bundle of the orbifold, because in fact, you can define the tangent bundle of an orbifold, which will be also an orbifold, right? So you have an action on a tangent, on the tangent. let's say on the tangent bundle, which also is given by the action of the group. So it leads to an action on the tangent vectors in the tangent bundle. So this in fact means that this is in fact a section of a orbifold tangent bundle. Okay, so I'm not going to, yeah. So so today I would like to explain to you how these ideas can be used to give a new proof of the classical elimination of singularities of nilpotent points in dimension 2. So of course this is a very classical theorem which dates back to, let's say, to the beginning of the 20th century. So how's the classical proof goes on? So recall that you have this vector field, let's say A of the x, B of the y, and the idea is to eliminate all nilpotent points by sequence of, in this case, of usual blowups. So there is the original proof of Seidenberg. It's a quite intricate proof, making some study of the formal series. And now there is this quite geometric proof of van der Essen. You can look at the book of Yakovenko Lyashenko, but I think that the first paper where it appears in detail was the paper of Mattei Mossu from the 80s, if I'm not mistaken. Yeah. So what's the idea of this? Let's just give you a small idea, but to show that there's some drawback with this proof, in my opinion. So how do you do? So you take the coefficients of your vector field. So in this case, in fact, you're going to treat your vector field just as a pair of coefficients, right? So, well, it's not very natural because a vector field is more than just a pair of coefficients, but this is the idea here. So you take this function germs, A and B, and you have two numbers that are going to attach to this. So this first number is what we call the intersection multiplicity of the curves defined by A and B. So just the dimension of this this vector space here. So I suppose that A and B don't have a common factor in such a way that this is a finite number. And then there is mu, which is just the order of the ideal generated by A and B. So you just take the first non-zero jet of A and B, then you divide this mu, right? So the usual argument goes as follows. You use a thing which is called the Nether Formula, which in fact studies how this intersection multiplicity changes when you blow up a point where two curves intersect, right? So I'm not going to enter too much detail, but this formula gives you this identity here. So it says the following. So you take now the intersection multiplicity of your resulting vector field after blowing up the origin. So you take this M on each point, P tilde, which lives in the exceptional divisor. And then the sum of the intersection multiplicities is given by this formula here, where L is the multiplicity, let's say, on the original multiplicity if delta is non-dicritic. So I have called it, and it's given by the multiplicity, the order plus one if delta is dicritic. So I recall to you that the dicritic case is the case where after blowing up, all the points on the divisor yes, you have a whole bunch of singularities on the divisor, and in fact, upon after division by the highest power of the equation of the exceptional divisor, all points become singular, and most of them are singular points of elementary type. So this is the dicritic phenomenon. So there is this L which appears here. And of course, the argument goes as follows. If L is greater or equal than 2, then you can show that the intersection multiplicity strictly decreases, right? So this is a good case because it shows that the invariant goes down. But when L0 equals to 1, and so, well, this is, for me, it's one of the drawbacks of the equation, that then you fall in a special case, which has to be treated separately, because in this case, where L equals to 1, then the invariant can in fact increase, right? So let me just give you an example. So you take this, just this, so if you, this is a sort of new, Sorry, yeah.
Yes, sorry, that just mu of AB is equal to mu of 0. Is it?
Yes, I have to correct this. Yes, this is
Okay. So thank you.
Yeah, so this is a sort of generalization of the nilpotent situation that I've shown to you before, where m now is greater or equal than 3. And in this case, mu equals to 1 and a little m equals to great M, as you can compute. And now if you make a blow up, so this is precisely the case where this L equals to 1. And if you make a blow up, you find out this equation here, right? And you can compute that now mu increases and M also increases. Okay, so in some sense, you have to, this goes as a special case which has to be treated separately. And well, for me, it's never a good point. Let's say it's never a good sign where some case has to be treated separately, because it says that you have to, in some sense, to control when you jump from one case to the other, and this is quite delicate when you have this kind of argument to control these jumps, because you have to prevent the case where you jump, let's say, infinitely from one case to the other. And so now I'm going to explain to you, so this is the goal of today's course, how to prove this result using weighted blowups. So I'm going to show you a modified version of a proof which has appeared in the thesis of Michel Pelletier, a student of Robert Rossari. So it goes, it's a little bit, from my point of view, it's quite a nice argument, because as I said, it's a case where you don't have special cases. Everything fits very nicely in a single inductive argument. So the initial setup is this: you have this two-dimensional real analytical manifold. I go to make things in the setting of manifolds with corners, because it's a little bit simpler. You don't have to keep track of the orbifold structure here. Okay. So now E, as I said, the divisor which appears here is you can see it as the boundary of your manifold with corners M. And the hypothesis that you have a foliation which is tangent everywhere to this divisor, right? And also that the nilpotent locus is of codimension 2. Recall this was one of the assumptions that I've made before, but of course in this case it makes things a lot simpler, because in this case it means simply that the nilpotent locus consists only of isolated points, right? Because you're in ambient space too. So for us, the local desingularization strategy will correspond to assign to each point P, which is on the nilpotent locus, a choice of quasi-homogeneous filtration of the local ring. So this quasi-homogeneous filtration is the filtration which will dictate the weight of the blow-up that are going to choose on this point, right? So of course, the algorithm consists on the choice of this blow-up, of this weighted filtration. And now I'm going to explain how to choose this. But for this, I need to make a small intermezzo by talking to you for this very general concept of a Newton polyhedron for a vector field, right? So now I'm going to place myself in the any dimensional case. And let's define this object here, because it's will be in some sense our guiding combinatorial object all along this procedure. So we fix local coordinates on a point, on a manifold, and we can write a vector field in this expansion. But as I said to you, everything will be much easier if you use this logarithmic basis, right? So instead of taking this expansion, I'm going to write a delta is b1 d over d1, etc., plus bn d over dxn. And of course, now I have to admit the fact that this bi can potentially have poles along the divisors x1, x2, or xn. So it's I'm going to see that in fact it's a quite natural phenomena here because, well, I want to see it a little bit later, but you have to admit this possibility. And now we're going to do the following thing. You take this expansion, right? And I'm going to reorder it in the following way. I'm going to put the, let's say, the emphasis on the monomials, right? So I can, for each one of the monomial x to the power k, so this is, of course, the multi-index notation, I'm going to expand the vector field which multiplies the x to the power k monomial, right, as a diagonal vector field of the form of mu1 d over dx1, mu n dxn, and so on. Okay, so in this new expansion, you have this xk times, for each one of the x to the power k, a monomial vector field which coefficients mu1, etc., mu k. Okay, so as I don't know if you recall, I've said to you that this diagonal vector fields can be seen as an element of what we call a toral, an abelian subalgebra of the algebra of vector fields, a C abelian subalgebra, which is simply the algebra generated by x1 d over xn d over dx. So in fact, later on, we are going to make this algebra change, because by choosing another coordinates, of course, you are going to change the. So this algebra is uniquely attached to the choice of coordinates. So changing the coordinates, in fact, corresponds to the changing of this Lie algebra here, right? And then, of course, it corresponds also to the change of the monomials and so on. Okay, so now you have this monomial expansion, right? And you define the support of your polygon of your derivation with respect to the coordinates as the set of indices k such that the corresponding diagonal vector field has non-zero coefficients. And finally, you define the Newton polyhedron as the convex envelope of this of the support Minkowski sum with the positive quadrant. Okay, quite classical. Let's say in the cuspidal case that has guided us up to now. So you have this initial form, and then we force the appearance of the logarithmic terms here. And as I said to you, now we have these two meromorphic monomials here, right? So x to the power minus 1 on the first term and y to the power minus 1 in the second one. And now you plot this these points on the plane, right? So we have a monomial minus, let's say the point minus 1, 1, which corresponds to the first monomial, and 2, minus 1. And as I said to you, there's the eventual contribution of these monomials which come from the first term, but they lie inside the Newton polygon, right? So the main part will come from, which corresponds to this edge, will come in fact from the first two, the red colored terms here, the Newton polygon, right? So the rest term, in fact, it does not affect the resolution of singularities procedure. Okay, so just some remarks. So as I have seen here, this Newton polygon can have negative vertices, right? Because of the appearance of these negative exponents here. But in fact, if it's attached to a vector field, then you can show that it's always contained in this convex region that I've colored here in red. So just take so let's say the black lines here correspond to the positive quadrant on z to the power n, on r to the power yes, and then the eventual negative vertices which can appear on the Newton polygon of any vector field will necessarily lie on this at worst on this red region which we are here. So the Newton polygon is always contained in this in the region which is to the right and to the up of these red lines here. Okay, so later on I'm going to talk to you about the Newton polygon of any differential operator of order possibly greater than 1, and of course in this case you can have more negative terms here. But in the case of vector field, which order one differential operators, it always lies in this region. So second remark, you can see from the device, let's say from the support of the polygon or the polyhedron, whether the hypersurface, let's say xy equals to 0, is invariant, because it simply corresponds to the fact that the support should be contained in the positive, the region where the ki, let's say the xy coordinates are all positive. Right, so I'll give you an example in a moment. And the hypersurface is tightly invariant. So I recall to you that tightly invariant is the case where it's invariant, but it's not entirely formed by nilpotent points. So this corresponds to the fact that, let's say in this case, if you want to see that let's say if the coordinates are x and y, if the x coordinate, the x plane is invariant, it means that the polygon should be on the positive right part, right? But it's not true to the right. So it means that it's contained on this let's say in this hyper, how to call it? Yes, this region here, this hyperplane region, but it has points which are contained also in the hyperplane Ka equals to it's not empty, right? So just an example. Suppose that you start with this vector field here, right? So I said to you that the y-axis is invariant if and only if. So this is by definition. The derivation preserves the filtration given by the ideal x, right? So it maps this, but this corresponds to see that. So if you force this, of course, this logarithmic expansion, this corresponds to the fact that the a which appears here should be an analytic function, right? So it's not, it don't have poles along the y-axis, but this, of course, corresponds to the fact that the support of the Newton, let's say the support of delta in these coordinates should be of the form k and l with k greater or equal than 0. But it's in order to be not tightly invariant, then in fact this should correspond to the fact that the delta, you should translate the filtration by x powers by 1 unit. So we should have something like this, right? By definition of not tightly invariant. But this corresponds precisely to the fact that all points on the support KL should satisfy the condition that k is greater or equal than 1, right? So if you draw this line here, you see that this first, let's say, dashed line here, the leftmost dashed line corresponds to monomials which k equals to 0, and the second dashed line corresponds to monomials with k greater or equal than 1. So if the polygon is contained on the region which is on the right of this leftmost dashed line, so the line x equals to 0 is invariant. Okay. But it should not be to the right, too much to the right, because otherwise you should have this condition that we don't want to appear. Yeah, so I think this will be the oldest reference that we can find in this course. So okay, so Newton used this idea of polygons to solve polynomial equations, right? So the idea is to capture with this polygon, as this polyhedron, the best quasi-homogeneous filtration in order to, let's say, to simplify your object. So the resolution of singularities should correspond to a combinatorial game, which is based on the Newton polyhedron, right? So this is very classical to the case of functions, and now we're going to apply it to the case of vector fields. So first thing is this one is quite important. How can we recognize that we are in a final situation, by which I mean an elementary germ, just by looking at the nilpotent, just by looking at the Newton polygon, right? So of course, intuitively, if this polygon is too far from the origin, the singularity should be complicated. But how do you make this intuition precise? So in the case of vector field, there is a very nice correspondence, which is the following one. So a derivation is nilpotent if and only if there exists a local coordinate system such that in these coordinate systems, you can separate 0 from the polygon. Right, so I mean that there is a coordinate system such that you can find a hyperplane which separates the origin from your polyhedron. Okay, let's just give a proof of this. It's not very difficult. So let's suppose in one direction that 0 does not belong to the Newton polyhedron, and such an appropriate choice of coordinates. So you can find some non-zero vectors, rational vectors. Okay, so everything will be rational here because the vertices of your polygon are points on an integer lattice, right? So in fact, your polygon will be defined by rational inequalities, right? So everything can be done in this field. So you can find a weight vector omega and a positive rational number alpha, such that the Newton polygon is entirely contained in this half space here, H, given by all points which satisfy this inequality here, right? So this is the separating hyperplane here. And of course, all the coordinates, all the entries of omega should be positive or 0 because of of course, by construction, all I've taken it in order to define the Newton polyhedron. I've taken the Minkowski sum with the positive quadrant, right? So you cannot have a separated hyperplane with negative entries, which is quite simple to see. And of course, I'm assuming that it's a non-zero vector. Okay. Now, once we fix this weight vector, right? So you can define the quasi-homogeneous graduation of the local ring, which is given by the torus action. Sorry, of course, we can up to elimination of a common denominator. We can suppose that all entries of omega are integer valid, and so we consider this torus action here. Okay, and of course, this will be the torus action which will allow us to prove the nilpotency, right? So there are two ways to see this torus action, either by let's say, in order to see the graduation associated to torus action, either by the torus action or by the infinitesimal generator of this one parameter group, right? So if you take the infinitesimal generator of this, just derivate this with respect to t, you get a semi-simple vector field, which is a diagonal vector field, which is given by this expression here, right? So the same weights. So okay, this action is diagonalizable as an action on the local ring, and you have a direct sum decomposition of your local ring in a sum of graduated pieces, where each piece is simply given by let's say the germs of functions which are omega quasi-homogeneous of degree alpha, where alpha is the degree. Okay. Well, using also the semi-simple generator, you can define this as exactly the same graduation, either by taking a germ f and taking its derivative with respect to the derivation delta here, and it's quasi-homogeneous, omega quasi-homogeneous of degree alpha, if it satisfies this equation here, or either, which is equivalent, if it's the action of the torus satisfies this relation. Okay. It's better. I think it's better to work with the second point of view, because it's easier to make computations. Okay, so now, in fact, this action also induces an action on the derivations, right? So when you have a group which acts on the, let's say on the ring of functions, it also acts in the endomorphisms, which act on this. Let's say let me just take it back. So if you have some group which acts on a vector space, it automatically acts also in the endomorphisms on this vector space by conjugation, right? So the action of this one parameter group on a derivation, seen as an endomorphism on the local ring, is just given by conjugation. So now it just means the following thing: you take a germ f on the ring, you make lambda t minus 1, and then apply the derivation, and then apply lambda t. So that's a classical action by conjugation. Right? So this gives a new vector field, and of course, this gives you the torus action on the derivation, and induces also a decomposition like this, right? So a direct sum decomposition, where the graduated piece of degree alpha are the vector fields delta, let's say, such that these expressions gives you are equal to t to the power alpha times delta, right? Okay, so there is this graduation on the vector fields, there's graduation on the functions, and of course they are compatible in the sense that when you apply a graduated piece of degree alpha of vector of derivation and a graduated piece of degree beta, and then you have something of degree alpha plus beta. Okay, so in these coordinates, it's very simple to see what I mean by graduated piece. So sorry, yeah. So you just take here. I look at the Newton polygon of delta. So in this Newton polygon, you have it's graduated. It lies on the graduated piece of degree alpha if its support is entirely contained on this hyperplane here, right? So this is this. So you see that in fact, when we make this hyperplane, you translate this hyperplane parallelly on the same direction. You get all the graduation. Yeah, so let me just go back to our definition. So at the beginning, sorry, our argument. So I suppose that the Newton polygon is contained on this region here, right? So in fact, it corresponds precisely to the fact that the support, so the fact that support is contained on this region means that all graduated pieces of delta are of degree greater or equal than alpha, right? So this is a notation for the filtration associated to the graduation. So this means that all graduated pieces of delta, are contained are of degree greater or equal than alpha. Right? So they're above this hyperplane here. Okay, so since this is a filtration, it means that delta square is, so now delta square is no longer a derivation, but it's let's say an order 2 differential operator, but it also acts as an endomorphism on the local ring, right? So it's you can calculate delta square, delta R, and so on. So you get, of course, by the property of the graduation, the R iterate of delta lies on the graduated piece of degree R alpha for all R. And it means that if you look at the support of the R iterate of delta, it goes upper and upper here, right? So in fact, if you take any germ f of degree greater or equal than beta, and you apply delta to the power R, you get something which is of degree greater or equal than R alpha plus beta. But as a consequence, if you take the local ring, so you apply this delta to the power R to each element of the local ring, you see the following things. For each integer S, there exists an R such that the R power of the R iterate of delta applied to the S power of the maximal ideal lies on the S plus 1 power of the maximal ideal. because of this argument where you increase the graduation, right? So it means, as if you remember, it means precisely that delta is nilpotent because it increases the order of the maximal, the powers of the maximal idea. Okay, so this is a small argument to show why this why this S exists for each R. It's well, you have just because of this small inequality here. Okay, so we have proved that if there is a separated hyperplane, then delta is nilpotent. Now the reciprocal is, I think it's interesting to prove the other direction because it explains to us a technique that will be very useful. So now assume on the other direction that delta is nilpotent, right? So by this I mean that it preserves the maximal ideal, and then the semi-simple part is 0. Right? So by the classical Jordan normal form theorem, you can suppose that up to a linear change of coordinates that the action of delta on the first jet is given by a matrix of this form here, right? So just a lower triangular matrix with 0 on the diagonal, right? So this means that when you apply to the coordinates x1 up to xn, it should have a form like this, modulo m to this m2, right? So, and just normalizing the first jet, where this epsilon are either 0 or 1. So when you look at the expansion of delta in the logarithmic basis, it means that it should be something like this. Okay, so this epsilon I, which is 0 or 1, times x to the power I plus 1, xi plus 1, xi to the power minus 1, times the logarithmic term on xi, d over dxi, plus some rest, where the rest is a derivation of degree greater or equal than 1 with respect to the usual quasi-homogeneous filtration. So here, in fact, when I write this expansion, you see that this first term, so there is xi plus 1 times xi to the power minus 1, and this term here, sorry, yeah, I cannot show it. Yeah, this term here is homogeneous of degree 0 with respect to the usual homogeneous filtration, right? Because it gives weight, the same weight to each variable. And now I'm, well, yeah, so the rest term here should be of homogeneous degree greater or equal than 2, in the sense that each monomial which appear on this rest term R should be of a sum of expressions like this, but with the sum of where the sum of the exponents should be greater or equal than 1. Okay. Okay, so now this is the usual filtration. Now I'm going to recall that I want to find a separating hyperplane, right? So this will not be a separating hyperplane, but now I'm going to add a perturbation. So the perturbation is given by this weight vector here, right? So it's, well, I'm just writing the case where n is even, but when n is odd, you just take the integral part of this term. So in fact, any rational vector which satisfies these two conditions will do, where ay is the I element of the canonical basis. And I claim, I'm just explaining this by a drawing, but I claim for all sufficiently small epsilon, the derivation is given by h plus epsilon times the diagonal derivation with these weights will be a separating plane. It separates the polygon from 0, right? Why this is so? Well, it's very simple, in fact, but well, I'm not going to explain this, a very simple argument, but I'm going to explain by a drawing. And well, this illustrates some tool, some technique which I call the Hinge method, which is the following. So I start with this nilpotent configuration, right? So x to the power minus 1 y, x d over x. So two variables just to simplify things. So it means that if you look at the support of the polygon on the initial part, it's just given by this red circle here, right? So there is no other point on this first line here, except for this red one, right? So what we do is the following. You take a weight vector here, rho, which is just the blue one that I've written here, I've drawn here, right? In this case. Yeah, so, well. And now you take h plus epsilon times rho, right? So this will be my omega. And now what happens when you make epsilon positive, right? So it's just like if you put a hinge, charnière, no? A hinge here in the red point. And then when epsilon growth increases, you see that the black hyperplane, it goes like this, right? And for epsilon sufficiently small, you cannot attain the points which are on the rest. But yes, because let's recall that the other points on the polygon, which are not of degree 0, let's say, which are not on the red line, will be at a positive distance in such a way that if epsilon is sufficiently small, you don't touch them by the separating hyperplanes, the separating hyperplane defined by omega. So in fact, you can separate them by this perturbation. You find a plane, let's say a weight omega, such that it's what I've written here, delta lies on the strictly positive graduated piece with respect to omega.
Yes, sorry, Daniel.
Yes.
Here, epsilon is what? It's a rational number?
A rational number, yes.
Okay.
Yeah, of course. I work always in the rational case. So epsilon is strictly positive rational. And of course, when I get this thing, is I can normalize to have an integer evaluated vector. Okay. Yeah, okay. So there is another proof of one of the implications of the theorem, which is quite, I'd say, informative for me. It's the following thing. So suppose that delta is elementary, by which I mean it's not important. Then I claim that for all choices of coordinate system, 0 will always belong to the Newton polygon, right? So in the case where the singularity is elementary, or the germ is elementary, you can never separate 0 from the polygon, despite of the choice that you make of the coordinates. Okay, so let me just give a short proof of this. So this proves an alternative proof of one of the directions of the theorem, the first direction of that I've proved to you. So the hypothesis that it's elementary means that either the maximal idea is not preserved. So this is the case where you have at least one coefficient of your vector field which not vanish on a point, the flow box situation, or in the case which preserves the maximal ideal, the semi-simple part is non-zero. Okay, so let's consider just the second case. So, well, I think this can be a nice exercise to prove that in the second case, this one, you can always find a germ F, but in this case, a formal germ, possibly, such that this equation is satisfied from some unit U, right? So it's a sort of eigenvector for the delta, right? In the sense that it's delta maps F to itself modulo multiplication by a unit F. And you can think of this as saying that F is an invariant hypersurface for the derivation. Okay, so assume that you have this. So let GR be any graduation defined by an arbitrary one parameter group. So take any derivation, so in any coordinate system. And then, of course, since F, yeah, so suppose that F lies of the graduated piece of degree greater than alpha for this graduation here, associated to this group lambda. and such that delta lies on the graduated piece of degree greater or equal than beta. So as a consequence, delta F lies on the graduated piece of degree alpha plus beta, degree greater or equal than alpha plus beta. Okay. But of course, all unities should have, let's say the constant should have graduation 0, right? So yeah, so this I have to precise this because yeah, I'm just talking here about one parameter group with positive weights. I'm sorry, I have to complete this because. But so by the above choice, since you have alpha plus beta should be equal to alpha, and as a consequence, beta should be equal to 0, right? So any plane which is defined by the plane which is defined by the graduation lambda should be such that delta lies on the 0. Let's say should have a component in the 0 graduated piece, right? So it means that you cannot separate the origin from the Newton polygon of delta in this graduation. Well, the case where the delta doesn't preserve the maximal ideal is even easier, because in this case, in fact, you can prove that this property here corresponds to the fact there always exists a term on the, let's say, a monomial or a vertex of the Newton polygon, which lies on one of these points here, or more generally, one of the points of the form minus AI, EI, where E is the term of the canonical basis. Okay, so yeah. So the important part is that if you have a quasi eigenvector in this sense that I've written here, it's impossible to separate the Newton polyhedron of delta from the origin by a positive evaluation, by a graduation, by a hyperplane. Okay, so just an example here. You take as our old friend the nipotent cuspidal case, right? So in this case, you take, as I said to you, the graduation associated to the degree 2, 3, and you see that delta is contained in the graduated piece of degree greater or equal than 1 with respect to this graduation. Why? Because when you write in the logarithmic basis, you see here appear x to the power minus 1 y, right? So this term here has degree given by 2 times minus 1 plus 3, so 1, and this term also has degree 4 minus 3 equals to 1. Yeah, so geometrically you see that this red line here, which is the line which is orthogonal to the vector 2, 3, separates the polygon from the origin. And as I said to you, you have to choose the coordinates correctly to have the separation property. For instance, if you take the same example and make the linear change of coordinates, y goes to y plus psi times x. So what's the action of this change of coordinates in the polygon? In fact, it slides the monomials along the direction 1 minus 1, as I've drawn in this bottom figure here, right? So in these new coordinates, you will not see the separation from of the polygon from the origin, right? Because in this case, then there will be this edge which will contain the origin, this interior. So in this sense, it means that these new coordinates do not witness the nilpotency, but there is a system of coordinates where you can separate them. So for those of you which know what's called the geometric invariant theory, this is very similar to a result which appears in the geometric invariant theory, which is called the Hilbert-Mumford criteria. Okay, I'm going to to push a little bit further this analogy, you're going to see that it's in some sense it gives you a criteria to define the notion of elementariness for differential operators of higher order. Okay, so let's go back to the proof in dimension 2 with this tool. So you have this initial setup of so you have this initial setup where you have this triple manifold with corners, and then there is a boundary E with a normal cross divisor, and F is a foliation tangent to E. And now at each point, so at each point on the boundary, you have either two components, right? So two locally reducible components of the boundary which cross on this point, or just one. And I'm going to, so there is this number E of P for each point P, which counts the number of local irreducible components of the divisor of the boundary of the divisor at this point. Okay, so since we want to have centers of blow up which will have normal crossings with the boundary or with the divisor, we're always going to work with this concept of adapted coordinate system. So a coordinate system, let's say in this two-dimensional setting, is adapted if the divisor is given locally either by x equals to 0 in the case where it has a single component, or by x times y equals to 0 in the case where we have two irreducible components. So in the case where you have just one component, a coordinate system is adapted if this component is just given by the vertical axis in this coordinate system. So now there is let's say a simplifying initial step, which is not completely essential, but it will simplify a little bit the argument, which is the following. We are going to suppose that all nilpotent points are included in the boundary or in the divisor. Okay, so suppose that the set of nilpotent points is contained on the boundary E, and if this is not the case, I can force this by just blowing up these points, since this is formed by a discrete set of isolated points. I can just blow up these points in order to include them in the boundary with an arbitrary weight. So in this case, in fact, I don't like very much this initial simplification because it's a sort of artificial initial step. But in any case, you can always suppose this, and it gives you, let's say, a simpler argument later on. Right, so you include all points on the divisor, all nilpotent points on the divisor by just blowing up them with any weight. And now you have this hypothesis which holds. And in fact, there's a second hypothesis here that I'm going to make just to simplify the argument. But you can get rid very easily of this hypothesis. So I'm going to suppose that at each nilpotent point, the number of irreducible components is equal to 1. Right, so they are in the divisor, but they are not initially in the crossing of two irreducible components of the divisor. So they're not in this, let's say in this. You don't have E of P equals to 2 at any nilpotent point. Of course, this is always true if you start with an initial situation where the boundary is empty. You start with a boundaryless manifold, and then you just apply this procedure of including the nilpotent locus in the divisor by blowing up. And in this case, of course, you just get this condition automatically at this first preparation step. But even if this condition is not true, you can easily treat the case where the points are on the crossing of two components of the divisor by modifying the invariant that I'm going to show to you, by including this number E of P lexicographically in the expression of the invariant. Okay, so now how does it go? So you suppose that the point P is on the divisor, right? And now you're going to work exclusively with this adapted coordinate. So if you try to expand the Newton polygon to express the Newton polygon of the derivation on the point P with respect to these adapted coordinates, it should necessarily have a form like this. Why? Because as I said to you, the divisor x equals to 0 is invariant. So by this, I mean that all the polygons should be on the right of this vertical line given by here. So there is no points on the support which have a negative first coordinate, right? And well, I can formulate this by saying that the invariance of x equals to 0 implies that delta should lie on the positive graduated piece of the derivation with respect to this, with respect to the graduation defined by d over dx, right? So it's the same thing as I said to you, but just formulated in terms of this graduations language. And now, on the same side, since I suppose that the divisor is not entirely formed by nilpotent points, right? So this there is a main vertex. So that this is the, let's say the leftmost vertex of the polygon, which should lie on the line, on the vertical line given by first coordinate equals to 0. Because otherwise, if it's to the right of this point, then you should have a divisor formed by nilpotent points, right? So this main vertex corresponds to, let's say, to a monomial vector field of this type. Sorry, this is y to the power h. I made a mistake here. This is y to the power h. Okay, and now, so this is true for any point on the divisor, but I claim that the point P is nilpotent if and only if this height, the height of the main vertex, is greater or equal than 1. Okay, why this is so? Because, well, so if 0 lies, let's argue by, on the other hand, so if 0 lies on the Newton polygon of delta, then the initial quasi-homogeneous part of delta with respect to weights 1, 1. So I'm just taking this, the line the line given by the graduation 1, 1, right? So it should be either one of these forms. So when the height is -1, you shouldn't have something like this, right? So it means that you had a point on the negative second coordinate, h, or a point of this form, right? So what is the initial form of this type? Initial form of this type means that you have 2 points on the support. So the first point, so the first term here corresponds to the point at the origin, and the second term, which can perhaps it exists or not, corresponds to a point which is on the has a coordinates 1, -1, right? So it's in the downstairs here. But okay, so for some constants A, B, and C, but in the second case here, I can guarantee that A and B cannot be simultaneously 0, because otherwise you should get a nilpotent situation. Sorry, because if they are both equal to 0, it would mean that you don't have this point on the origin lying on the support of the Newton polygon. But this is not true, because we know that there is at least one point of the support which lies on the vertical line given by first coordinate equals to 0. Okay, so this pair A, B is different from 0, right? So in the first case, I'm claiming that in the first case you have of course a regular situation, a flow box situation, because you see that here your vector field is essentially just y d over dy, just a vertical vector field. And in the second situation, this, you see that this is if you write the Jacobian matrix, or let's say the linear part of a vector field, you just have a triangular form. It's just a triangular matrix. And so the spectrum is given by just these coefficients A and B, but since they are not equal to 0, both, then there exists at least one non-zero eigenvalue, and by which I mean that the semi-simple part is non-zero. Okay, so I've proven that if the height, yeah, so so if 0 lies on the, this is just the part that are going to be needed, but it's if and only if condition. But if 0 lies on the nilpotent, on the Newton polygon of delta, then you are in an elementary situation. So the goal, of course, is to make this main vertex goes down, its height must go down, right? Okay, so now it's quite easy. I have time to finish this today. So the main invariant, as you can imagine, will be this height h. And in fact, it's an invariant because it does not depend on the choice of adapted coordinates. If you take two different coordinates which are adapted to the divisor, it will give you exactly the same height. Why this is so? Oh, sorry, because suppose that you have one of these adapted coordinates, and if you consider the automorphism which maps one adapted coordinates to the other one, so it should be of this form. So it should preserve the x equals to 0 divisor. So it has to be able to factor out the x on the first component, and then on G is let's say in the second component is an arbitrary change of coordinates, where f is a unit and G is like this. Okay. And in fact, it's easier to see that by looking at the Lie algebra. So these automorphisms which preserve the adapted coordinates are automorphisms which are generated by whose Lie algebra is generated by vector field of this form, right? So, well, it's like a sort of general type of vector field, monomial vector fields, but with the condition that yes, so the k which appears here should be strictly positive or 0, right? So it guarantees that when you integrate this types of vector fields to the time one flow of these vector fields will give you the group of automorphisms, and the condition on k, which I put it here, corresponds precisely to the fact that you can have an x which factors out, right? So other way to see that is that this Lie algebra lies in the intersection of the positive graduation with respect to x and the positive graduation with respect to x over x plus y over dy. Okay, well, as always, it's easier to see this by a drawing, but it means the following. If you take the support of the germs which satisfy this expression, this support should lie in the region that I've written here. So it's above the line corresponds to the derivation, to the graduation x dx plus y dy. So it's above this diagonal line. And it's to the left of this vertical line corresponding to the graduation x dx. Okay. So the only monomials which can be touched by this kind of transformation are the monomials which are on this region, right? So if you take this is the leftmost drawing is the support of the monomials which appear on this automorphism which preserve the x equals to 0 divisor, right? But when you apply this to the vector field, you see that its effect is just to slide the monomials along the directions which are, let's say, illustrated here in this rightmost drawing, right? So you see that you cannot touch the height because everything that you can touch either will be to the, let's say, to the upper side with respect to the height, or to the right of the main vertex. And it shows that perhaps it will be a good exercise to put this argument in a more precise term, but it's essentially saying that this kind of map. Well, if you start from this expression, it's quite easy to see that you cannot change the height by the action of this group. Okay. Okay. So now this is so this height is an invariant, and now there is a final touch, which is in fact the essential argument in all this stuff, and which will in fact be the ingredient which has to be generalized and adapted to the case of dimension 3. Okay, just going to here. So you have this main vertex, and now you have to read from the polygon which is the local strategy of blowing up, right? So which is the weight that you're going to choose to blow up your point in order to reduce the invariant, in order to reduce the height. So of course the natural choice here is to choose the following combinatorial in the following combinatorial way. You just take the edge starting from the main vertex, which is not vertical, right? So this is the edge with I've noted it by E, and now you take a vector of integer numbers with no common factor alpha beta, which is both components are positive, and now you would like to blow up with the weights defined by this alpha and beta. Okay. So the weight associated to the main edge is just the alpha and beta, which defines the supporting line of this main edge here. Okay, so now it's very easy to understand how this how the Newton polygon changes when you make a blow up with this weight, right? So how it goes. So we start. So the leftmost part here is the original polygon with this edge E. Now you make this monomial change of coordinates. X goes to the power x to the power alpha, and y goes to the x to the power beta y, right? So
excuse me, Daniel,
yes.
can you come back to the definition of the H,
Yes.
of the main H?
Yes.
There is something, you need to put some I somewhere, no?
Sorry, where?
Yeah, but because you put, just depends on J and not on I.
No, sorry, no. Here I just defined a little bit. Yeah, I said the following thing. So you have this Newton polygon, and
Yes.
now you just look at the intersection of this Newton polygon with a horizontal line, which is on the height h minus 1/2. Okay, so you take this this intersection, and of course, when you intersect a convex set with this hyperplane, you get a convex set defined on this line, on this horizontal line. And now, well, I think that the point which lies on this intersection is what defines the direction of the main edge. I'm doing this because when we're going to treat the three-dimensional case, in fact, you have a polygon, a polyhedron of dimension 3, and you have also main vertex, which is on some height. And in order to define the main face, you're going to cut this polyhedron by a plane which lies on the height h minus 1/2. Okay, so I'm just preparing for the generalization in the case of three-dimensional case. In the three-dimensional case, you're going to, when you take this intersection that which is in blue here, what you're going to see in this cutting horizontal plane is a new polygon of dimension 2.
Okay.
So,
yeah. Thank you.
So as I said, it's very easy to understand combinatorially what happens when you blow up with these weights, because so this first step is when you look in the let's say in the plane of monomials, it just corresponds to a shearing transformation where this blue edge becomes vertical, right? So it becomes vertical, well, the point which is on the intersection of this line, it's fixed, what's this shearing transformation, and then we make this division, which eliminates, let's say, which prevents the divisors from being an nilpotent log, which is division by R. And of course, the effect of this is just making this line gets back to the vertical axis here, right? And so these two first steps are completely combinatorial in the sense that they only depend on the configuration of the Newton polygon. But now there is a last step which corresponds precisely to the fact that you don't, when you make these two steps here, you're just centering your coordinate systems on the point which is on the origin of the, let's say, of the x directional coordinate. But since you want to study all points which appear on the divisor, you have to allow this kind of, sorry, this is y, should be y here. This last transformation, which corresponds to a translation to an arbitrary point of the divisor. Okay, so this is should be y goes to y plus psi here. And this last operation is not combinatorial because, in fact, it depends when you study the Newton polygon, which appears after this transformation. It depends on the expression of the vector field, not only on the combinatorial data here, right? But the effect, in some sense, it is to slide the monomials vertically like this. So this is the hard part which we have to control. Okay, so of course we'd like to prove that when you make these three steps, the height at each point which appears on the exceptional divisor, on the, let's say, on the inverse image of P by the blowing up map, should be strictly smaller. Okay, the invariance should decrease. Okay, so this, as I said, this is obvious for the point which lies on the origin of your x directional chart, just because it's a projection, right? So since there is this edge should start on the main vertex and finish on the vertex which is strictly lower here. When you project this, let's say, when you make this shearing and then you project the shearing and then you project back on the vertical line, you should finish with a main vertex which is strictly lower, right? So this is obvious if you don't make translations, but when you make this last sliding transformation, it can, sorry. When you make this last sliding transformation, you could have a full compensation phenomena, right? So I'm just giving an example of this, which shows that the height can be cannot increase. So okay, this expression should looks like a little bit too complicated, but in fact I'm going to show. We can obtain this by some sort of backward argument because it's chosen in such a way that the final example works, right? I'm going to show to you how to obtain this later, a little bit later. So you start with this vector field, and I claim that in this case you have a full compensation phenomena, which makes the height the same, let's say, which preserves the height. And in fact, this is a modulo multiplication by a unit. This is the unique family where this full compensation happens. Okay. Well, I think I'm not going to enter too much in the detail because I would like to finish this proof. But okay, so you take this. So you see here that there is this initial part, which is quasi-homogeneous polynomial of degree k times h with respect to the graduation given by giving weight 1 to the x variable and weight k to the y variable, right? So if you take this vector field, in fact, and you apply this omega as a Lie derivative to delta, you get k times h times omega. So this is precisely the same thing as saying that this delta is of degree k times h with respect to the graduation defined by omega. Okay, so now you blow up. So you blow up with, of course, with the weights 1 and k. I'm not going into too much in the detail, but you see that this initial monomial here will get an x to the power k times h, which factors out. And then here you get this expression, which it's not a very good sign, in fact, because you see that when you make the translation, y's go to y minus xi, this will be we just give you y to the power h, right? But of course, you have to study what happens to the term which is inside the parentheses. I've just written here the details, but when you do all the computations, you see that the strict transform of your derivation will have this form here. Okay, so let's say the coefficients are chosen in such a way that it guarantees this, right? So now you make the translation that I've said to you, that the last step, which is can be problematic. And when you make this translation, this monomial goes to x to the power h, and you conclude that the height doesn't decrease. So okay, so the algorithm doesn't work in this case. So why? How do you prevent this? In fact, to prevent this, you have to require something about the polygon, right? So in fact, this is the essential idea that I would like to explain to you today, which means that you cannot base your strategy on any choice of local coordinates. Recall that I said to you that in order to identify an nilpotent point, you have to choose a good system of coordinates. And now it's more or less the same. It means that in order to identify the good strategy to desingularize, you have to choose appropriately the system of coordinates where you're going to read let's say the weight of the blowing up. Okay. So for this, I have to require this condition of being stable. So I'm going to define first of all what I mean by a stable edge. So I would say that the Newton polygon of delta with respect to the coordinates x and y is edge unstable. If the following condition holds, you can find a change of coordinates, a polynomial change of coordinates of this form, okay, such that in these new coordinates x, y1, in fact you make the main edge transforms into the support of the main edge completely disappears except the main vertex. Okay. Okay, I want to make a drawing to explain this, but it means that up to this change of coordinates, you can make the main edge disappear entirely, except for the main vertex. Okay, and if you're not able to find this change of coordinates, you're going to say that the edge, the Newton polygon is edge stable, right? So, of course, since I've written this quotient here. The Newton polygon is always edge stable if beta over alpha is not a positive integer, right? So this condition is only, let's say, this such polynomial change of coordinates will only exist when beta over alpha is an integer number. And of course, let's say in the previous example, this was exactly the case where you have 1 and k as the weights here. Okay, so what do I mean by this edge instability? So you see that when you have this main edge here, so what's the effect of this change of coordinates? In fact, it makes the vertices slide along the line given by the main edge, right? So the idea is that if by all change of coordinates, which let's say which act on the main edge, if you're not able to eliminate all points except this, then the edge is stable. I'm going to give a geometric explanation for this in a moment. Yeah, I think I have time for this. Yes. Okay.
Sorry, Daniel.
Yeah.
Could you repeat what are alpha and beta, please?
So alpha, beta are the vertices of is the weight of
okay.
the orthogonal vector field of the orthogonal vector. Okay.
Thank you. Okay.
Yeah. So this is the line which supports this this edge here. Yeah. So now the claim is the following. So we're going to finish with this. This is the local resolution theorem. So suppose that you have a Newton polygon which is edge stable, and that you blow up with the weight which is prescribed by the weight of the main edge, the alpha beta that I showed a moment ago. Then for each point on the exceptional divisor, the height will be strictly smaller. Right. So of course you finish when we iterate this, you finish by attaining the situation where you when the height is equal to 1 or -1. I recalled you that you attain the elementary situation. Okay. Oh, so the proof is very simple. In fact, when you assume that you are in this situation, because, well, first of all, you don't have to care about one of the directional charts. So let's see what happens. Sorry, there's a misprint here. When you look at the y-directional chart, so the y-directional chart is a chart that instead of projecting on the horizontal axis, you project on the, instead of projecting the vertical axis, you project on the horizontal axis. So in this case, if you look at what happens in the point, which is the origin on the y-directional chart, you see that the main vertex gets projected on the origin here, right? So automatically, this point, which is the only point which is not covered by the other chart, you get the elementary situation, right? So the h tilde is equals to 0, so you don't have to care about this this chart. So the inter thing, of course, happens in the other chart. So in the other chart, you have, let's suppose by contradiction that you have, let's say that you have this monomial, let's say this blow up in the y direction, x directional chart. And suppose that you can find some point on the divisor where h tilde equals to h, right? So by this, it means the following, that you should find a non-zero constant, psi, such that when you compose this blow up with the translation y goes to y plus psi, the main vertex of the new polygon, the new polygon after blow up, should have the same main vertex, right? So just go back in a moment here. Yeah. So I called it, when you have this full compensation phenomena, the height should remain the same, which means that the main vertex should remain at the same position that it was at the beginning. So we split in two cases. So the first case is the case where beta over alpha is non-integer. This is the easiest case. And the case where b over alpha is a positive integer, right? So recall that in the first case, I said that the edge is always stable. But so what happens in the yes. So in the second case, you see that this polynomial map, this translation map y goes to y plus psi, it's quite easy to see that when you can map this transformation back in the original coordinates before blowing up, and it corresponds precisely to the map that I've considered when talking about edge stability. Okay, so just have to take the inverse of this monomial map, which is given by this, and then you see that this expression corresponds to this polynomial map in the original coordinates before blowing up, right? So this phenomena here, m tilde equals to m, corresponds precisely to the case where the Newton edge, so the original Newton polygon is edge unstable. but this contradicts the hypothesis of the theorem. So I don't know if it was clear. It means that if you interpret the full compensation phenomena that I'm trying to prevent in the original coordinates, it corresponds to the fact that you are able to eliminate all points on the edge except the main point here by a coordinate change of this type. Okay, but of course, I'm preventing this from occurring by asking the edge to be stable. Okay, so this is the first case. And in the second case, it's easier. Sorry, in the first case where the beta over alpha is non-integer, it's easier by let's say, a simple argument is the following. So if you look at the E initial form of delta, so the terms of delta which contribute to the main edge, you see that there should be a gap at height h minus 1. Why? Because if you look at the term which should appear at height h minus 1, it should be a point with non-integer coordinates. So there is no point here, right? So I just give an example here when b over alpha is equal to 2 or 3. Of course, here you see that there is no integer valued point at the line h minus 1. Okay. So the existence of this gap at height h minus 1 prevents also the full compensation phenomenon, because when you make the blow up and then the translation, this will necessarily, this is an argument. So when you make the blow up and then the translation, you see that when you change y to y plus any constant, this always will give you a contribution at least on the height h minus 1. Okay. So for you, which knows this is also old argument which Abianca called the lazy Tinhausen. Okay, the lazy Tinhausen is a sort of Tinhausen transformation for those which know, but where you create a gap just on this point and not on the whole line here. Well, so this is essentially the argument. I'm going to finish just to show you what's behind these two arguments here. It's quite interesting to understand this. So you see that there is this case b over alpha integer and b over alpha non-integer. And in fact, you can understand a little bit better this argument when you consider the case of functions. Okay, everything that I told you works also when you consider resolution of singularities of function germs, right? So of curves. So consider a function, a germ f, and I'm going to say that it's elementary when f is a unit. So this corresponds exactly to the case by analogy where 0 belongs to the Newton polygon of f. Okay, so this is in fact, in this case is invariant by the choice of coordinates. So the analogous condition to the case where of vector fields. Okay. So now, suppose in this case where you are in a function germ that you construct exactly in the same way the E initial part of your function. So the E initial part will be with respect to let's say to the alpha beta graduation will be something of this form, right? Where you have the main vertex, and then all monomials should satisfy this quasi-homogeneous condition here. And in fact, f of E, it's a sort of section of a line bundle over the weighted projective space of weights alpha and beta, right? So in the usual case where the weights are 1 and 1, this f is nothing else than the section of the power d of the d power of the tautological bundle. So you take this f of E, and I'm going to finish. Yes, you consider the divisor of this f of E, of this initial part. So what's the divisor? It's just a weighted sum of the roots of this monomial, where you attach the weight mi if this root is of multiplicity mi, right? So just to say simply, you just compute the expansion, let's say the factorization of Fe, and you descritize the multiplicities. And now the argument goes as follows. It's exactly the same thing that I've told to you with the Newton polygons. So the choice of F implies that this divisor has not, its support is not entirely given by the direction 1, 0, right? So it means that the existence of this edge means that the origin, let's say the point of coordinates 1, 0, has not all the multiplicity concentrated on it. So there is another root at least. Okay. Now, F is edge unstable if you can find another point which concentrates all the multiplicity, which is not the origin. Okay. So if there is a point of multiplicity, of maximal multiplicity H, the preparation, I mean, what you do is just that you translate the origin to this point. And then, so if this point exists, of course, it's necessarily unique because you have a root of multiplicity H. So there is a unique preparation which is possible. And okay, so this is the case where you can have a point of maximal multiplicity, which is not the origin. But I claim that when beta over alpha is not an integer, this is not possible. So in this case, you always have a preparation. Why? So my last drawing, because when you have beta over alpha, which is not an integer, the effect of translating the origin to some point, which is not the origin, corresponds to a symmetry, to what they call a symmetry breaking, right? So in this case, this function, f of e, should be alpha symmetric, right? So if you have a root, let's say xi, all other points which lie on the orbit of this point should be also root, right? So you cannot have a root which you cannot have a point which concentrates all the multiplicity, except if the action of the symmetry group is the trivial one. So, okay, I'm going to stop here. Thank you.